Chemical imaging combines optical spectroscopy and digital imaging to provide high-contrast images based on their molecular content. These images can detail sample morphology, chemical composition, molecular structure and analyte concentration, properties not always detectable in the visible spectrum. Also referred to as hyperspectral imaging, ChemImage is able to gather contiguous spectral bands on a per-pixel basis, spatially mapping the underlying spectral information in hypercube form. When paired with our powerful Spectral Suite imaging software, our liquid crystal tunable filters enable applications in precision agriculture, pharmaceuticals, semiconductor metrology, and biomanufacturing, just to name a few. How is it done? Let's investigate a specific example that demonstrates the power of ChemImage filter technology and analysis tools. Monitoring the chemical makeup and uniformity of a tablet during manufacture is necessary to ensure the medicinal efficacy of a drug. Uniformity must be maintained by checking that 1. The proper amounts of both active and excipient ingredients remain constant. 2. The particle size of each constituent drug remains consistent, ensuring proper release timing and dynamics during digestion. 3. The ingredients have maintained their proper form and have not changed during manufacture due to high temperature, production issues, or other environmental conditions. Chemical imaging is an effective at-line or research tool to develop and improve your process analytical technologies. Characterizing a sample tablet is straightforward with ChemImage's SWIR MCF and digital imaging software. Let's take a look at an Excedrin tablet, a common and well-known pain reliever for headaches. Using a broadband light source, infrared sensor, and ChemImage SWIR MCF filter with infrared optics, we step through the infrared spectrum at prescribed intervals, gathering spatial and spectral information. For the Excedrin tablet, the active ingredients are acetaminophen, aspirin, and caffeine. To ensure accurate data, we must also understand the environment in which the data is gathered. To do this, we reference the tablet's components against a 99% reflector. This will account for any variations in instrument response, including lighting, throughput differences, vignetting, and detector response. The result is a hypercube consisting of hundreds of two-dimensional images of Excedrin's ingredients, each at a different wavelength of the infrared spectrum. Now that we have the raw data on the tablet's active ingredients and the instrument response, we visually review it. This is a necessary step to ensure that you have good data, both sufficient signal levels and a sensor that is operating in its spec range. Because the instrument response dominates the raw data, note that the reflector spectrum and component spectrum appear similar. It's only when we isolate the spectra of the active ingredients can we observe critical target data. Removing the influence of the sensor spectrum from the spectra of the tablet's ingredients is relatively straightforward. This is quickly done by dividing the hypercube of those ingredients by the hypercube of the sensor. The result is spectra in terms of reflectance, which we convert to absorbance spectra for easier evaluation. An initial review of the spectra can be done at this time, noting the characteristic peaks of the Excedrin tablet's 3 active ingredients. Having made notes where the most prominent absorption peaks are, it's now time to select several wavelengths that can identify each of the 3 active ingredients of the Excedrin tablet. While we'll complete this exercise for all, let's look at acetaminophen as an example. Based on our experience, as few as 2 wavelengths can be sufficient for identification. First, we have to tell the software what's what. Because we're identifying acetaminophen, we look at an image in our hypercube and target acetaminophen by tracing a red box over the sample in the bottom left corner. We'll need to distinguish that from everything else, which includes the background and the other 2 tablet components. This is done by tracing a green box over the relevant areas. When complete, we put ChemImage software, Spectral Chef, to work. Using advanced proprietary algorithms, it chooses the best wavelengths for target identification, On the intensity graph shown, the greater the separation between the red target histogram and the green background histogram, the easier it is to identify the target, indicating a better recipe. This process is completed for all 3 active ingredients of the Excedrin tablet: acetaminophen, aspirin, and caffeine. Now that we know the wavelengths that will identify the makeup of our tablet, it's time to create the recipe. Each ingredient is identified with the wavelengths that were isolated in the last step, and together are viewed as a new material by our software. We proceed by importing these wavelengths and associating each detected pair with a false color. In this example, acetaminophen is red, aspirin is green, and caffeine is blue. With all of the identifying information now acquired and saved, we can make use of this new intelligence to identify the ingredients in an actual Excedrin tablet. The infrared image displayed is an Excedrin tablet cleaved along its short axis, exposing its interior. Applying the recipe results in the following false color image, showing the 3 active ingredients of the tablet, their particle sizing, and relative distribution. Areas of the image having no colorization indicate a lower correlation with the pure active ingredients and may be suggestive of active ingredient mixtures, excipient materials, and/or impurities. Thank you for your interest in ChemImage filter technology. To learn more, visit chemimage.com or email us at the address on the screen for further details about our filters and your specific application.